Hi everyone, Dr. Huckabee here. This is the second half of a lecture given in the spring, and it starts chapter 5. Chapter 4 was relatively short, so there's only really the one half of a lecture there. But chapter 5 is a fantastic chapter, and we're going to spend at least half a lecture and maybe more on it. So please have a look at it, enjoy the content. There's some really cool stuff about how our bodies use isomers of molecules. And without further ado, here is your to-do list. So your to-do list is to do the homework 5 assignment, finish reading chapter 4, and do as many of the problems as you can, as well as start reading chapter 5 too, because it's going to be very important that you get that information in your brain as we go through chapter 5 as well. So thanks everybody, and good luck.
Okay, so Chapter 4 has been all about isomers, right? We've talked about different types of isomers. We've talked about how to name alkanes. The last thing we'll talk about are what's called cis-trans isomers. And a cis-trans isomer, you think about whenever you are talking about molecules of cyclohexane, for instance, that have two groups. Let's just call them CH3 groups, just like your book does. So if you have two CH3 groups, how do you actually talk about where they are together? Are they both axial? Are they both equatorial? There's no indication given from this drawing, is there? It's all just nothing. So there's another kind of projection called a Haworth projection, and that projection is actually fairly useful for talking about cis-trans isomers of ring systems like this. So I'm going to do it in a pen because I find this a little easier. So you have, a Haworth projection. Draw it out. Haworth projection. Has the substituents coming up each side. So now if you're talking about CH3s, you can definitely tell, oh no, that's just way too thin. Let's stick with a Sharpie then. There we go. All right, fine. CH3s on either one side or the other. So you can see, even though these are pretty poorly drawn, how easy it is to see whether the CH3s are on one side of the ring or on the other. And we call these cis and trans isomers. Coincidentally, this is not the only type of cis and trans isomers that we have in chemistry. In fact, when you talk about double bonds, which we will do closer to the end of this semester, or even, I guess, later on this week or next week, or soon anyway, you have alkenes that can be cis and trans as well. Where this isomer here would be cis because they're both on the same side. And this one would be the trans isomer because they are on different sides. There we are. Does everybody see that? Cis and trans, same, opposite sides, fairly straightforward isomers. Okay, but that brings us to the end of chapter 4. Yes, questions? Yeah, it is. All right. Good, I like it. Keeping me honest. So this is the end of what I'm going to cover in chapter 4. Your book does give more details about other chapter 4E materials. a little more, but I've covered what I think are the highlights here because Chapter 5 is a little more, I don't know, important, exciting, interesting, especially if you have a bent, if your interest is more towards like biological chemistry or biochem or stuff that resembles organic chemistry that affects our lives. Chapter 5 is more important for sure. But before we move on, please tell me what questions you have for Chapter 4, because we have probably 5 minutes or so. We can cover some questions if you have them. When you have them. I want to hear them. Yes? Right, so the question was, which chair in the top left of the page, which chair structure is the same as the Newman projection? The chair on the left, the 5%, that is the Newman structure in the middle. I'll just circle them together here. So these two go together. Whoop, sorry about that. And these two go together. There we go. It all gets really jumbled up. I don't think I brought enough paper, so I'm trying to save. Yes? This is, yeah, it should have been, it is, so the question was, is the second one just rotating the carbon? It should have been a ring flip, I guess. That would have made more sense. It should have been where this guy was pointed up. So let me do it. Oh, that's horrible. So the second one should have been, thank you for catching that. Would have made more sense if it was the ring flipped version, because that's really what we were talking about, whether we have the one isomer or the same molecule but just ring flip to make the equatorial version. That would have been the better thing, and to draw that should have looked like this. There we go. And no, I did it again. I'm not great drawers, guys. Sometimes I get these wrong. So let's try it. I'm going to be really good this time. And I'm going to draw it. Oh, did I have it right? I might have. Yeah. Whatever. I'll draw it backwards, and then I know I'll have it right. There we go. So now this CH3 equatorial, and I'll just redraw the Newman projection. There we are. Red for the left side, blue for the right side. Now we have these guys that come out. There we go. That feels much better. So that's actually CH3. It should be up here. Where's my head at? I cannot get it together. There we go. Okay. So that should be the staggered version of the same cyclohexane. Okay. Thank you for that question. Please, other good questions. Yes. Yes, because it's still a bond line drawing, it's always CH's in the middle up here. So this brings up a good question, and something that I did notice in some other assignments. Please don't forget about bond line drawings and what they mean. In the test, which you will get the key back on Thursday, and in the homework from the resonance form, the biggest problems I saw were when I think you forgot what the bond line drawings meant and what each of the bond connections mean. So please remember, anytime you see two lines meeting, that means all the bonds you don't see, up to 4, are carbon-hydrogen bonds. So this cyclohexane has 2 hydrogens coming off of every carbon in addition to the bonds that are shown. Please don't forget that. That is super important for like the rest of this year of your taking organic chemistry, that you can just stick that in your mind and remember that carbon has 4 bonds And in a bond line drawing, the bonds you don't see up to 4 are hydrogen. All right, one more question before we go. Yeah. Okay, so the question was, in the Newman projection, which carbon-carbon bond are you looking down? Right? Because that's why we draw it as a circle, because you're looking straight down the bond. So, yeah, I should have drawn it. I have it on the other one, I think. Oh, I don't. That's fun. I don't. So when you see it, like on your homework, you will always see the I pointed at the CC bond that you're looking at. So if I were to go back and do this correctly, you would see that the I is pointed this way, down both of those bonds. In the same way here. You know, this structure was not a good one, but here the I would have been looking down these 2 carbons. Is that more clear? Yeah? Yeah, the I will always be there, that little thing. That way you know where you're looking. Sorry that it wasn't in these 2. I get excited, and then I start drawing way too fast. Okay. So that's it. Any more pressing questions? Yes, one more. Yes? Oh, okay. Okay. So here, like in this I, this this bond corresponds to this carbon. So that was the question. Which bond does it correspond to when you're looking at the Newman projection? And then this one here corresponds to that one. This is getting really crowded, like graffiti or something. Is that more clear? Yeah? Okay, cool. All right, so if that's all, that brings us to chapter 5. Chapter 5 is a great chapter. It's on stereoisomerism. And it's a really cool concept because just like in the beginning of the lecture today, we asked ourselves, do molecules have reflections? We saw that the answer was yes. And molecular reflections tell us if a molecule has what's called chirality. We'll talk about it in a little bit. But this physical property of chirality, being a non-superimposable mirror image of another molecule, can have big real-world effects. Here, these 2 molecules are part of the same medicine that you would get called methylphenidate. Methylphenidate is better known as Ritalin. Turns out, though, one of these molecules works really well. And the other one doesn't really do anything. But because it makes a lot more business sense to keep them both together, they just prescribe you a little more to make up for the fact that you have roughly the same quantity of the RR and SS in the medicine. That's a pretty benign example. I mean, what does it matter if one doesn't really do anything because there's not really any big side effects associated with it? But it can have big impacts. Probably the most famous of these ideas of stereoisomers giving much different results is a pretty sad one, actually. It's from a molecule called thalidomide. And I'm going to give you the very G version, PG version maybe, of what it does. One of the isomers was proven to stop you from having morning sickness if you're ever pregnant. And it worked really well. And it worked so well that, you know, in the 50s and 60s, Women were prescribed this by their doctors all the time. But unfortunately, the other stereoisomer caused birth defects. And just a warning, if you Google it, you will see what it does. So if you don't want to see that, just don't Google it. But it is pretty bad. And this is well-meaning. This wasn't done on purpose. It's just they didn't understand that these two things were so different. And that's why stereoisomerism can have such a big effect on our lives, because our bodies are chiral. You have a left hand and a right hand. You know, that's kind of like chirality. Your DNA, your amino acids, everything has chirality, and so our bodies respond to chirality in a much different way than they do to most other chemicals, because that means just like one hand can shake another hand, one stereoisomer can have a big effect, and the other one perhaps none. Right. So with that lead in, hopefully you're all totally wrapped and I have your attention after the snooze fest that was chapter 4. Just like you see up here, you see that we're now back to using wedge dash drawings for molecules. And it really matters because going back to like the beginning of the class style drawings, this molecule doesn't tell you anything except that each of the substituents, remember substituents? Yeah, the substituents, all these guys, are connected to the same carbon. But what they don't tell you is where in space they are. Just like when we were talking about conformers and cyclohexane, they don't tell you where spatially they might be located. So you could draw this potentially like whoops, CH3s. Like this. Oh no, that has too many dashes. Getting too excited. Calm down. Or, that's bad. No, I can't let that stand. You draw something poorly, just erase it and start over, right? So if we draw it this time in blue, because blue is my lucky color, then, here we go. I'm going to do it. It's going to be, all right, CH2, CH3, and the CH3. Great. So we can draw this molecule and its mirror image. Yep, its mirror image. So now this guy is coming out. This guy's straight ahead. Right, and these two molecules are not superimposable. They are mirror images. And what I mean by superimposable, I mean that if you could physically lift this structure off of the table and move it over there, it's clear that they would not be the same molecule. Do you believe me? Is it clear? What if we took a different molecule and we had a mirror and we shoved that molecule in front of the mirror and we saw again its mirror image? So now I want you to do, in your mind's eye, picture that you're going to hold this molecule by the chlorine. Okay? We're going to keep the chlorine where it is. And we're going to turn it like a top. So that the place where the ring is mirrors the place it is on the left. Or not mirrors. So that we can physically put the 5-membered ring on the right onto the left structure. And if you do that rotation, now hopefully you can see that the two structures are not superimposable. You can't put one onto the other and call it the same molecule. These are different. And this is what makes two stereoisomers, or enantiomers. Enantiomers are your big OChem as a foreign language lesson for today, because enantiomers are chemical twins. Same molecule, mirror images. Mirror images that are not superimposable. Just like beaker on the right, you can't take the R beaker and move him over to be S beaker. I mean, you can just look at those pictures and tell you can't do that, right? But in all seriousness, again, this is a chemical that is used in agriculture. Another example where the R enantiomer or S enantiomer works much better than the other. But if you just drew these out in the way we did before with no information, you would think they were the same. So just remember in your minds that just like beaker, these molecules are different. And we have to be careful of where in space they are. And you might have noticed I was talking about R and S. R and S are the systematic names for the stereoisomers that can result, the two types of stereoisomers, the enantiomers. They stand for rectus and sinistre. They are, sinister, that's Latin. We have a lot of weird stuff in organic chemistry because English was not organic chemistry's first language, so a lot of the abbreviations don't make sense in English. So R stands for like clockwise rotation, and S for counterclockwise. Your book covers it, and so are we. We're going to talk about how to find the configuration of a stereoisomer no matter what it looks like when it's given to you. Has anybody looked at this yet in the book? Has anybody seen the rules for how you assign priority, how you do the rotations? No. I'm seeing a lot of head shakes. That's unfortunate. It would go a lot better if you guys had looked at this before, but that's okay because there's time, and I really strongly encourage you to look at this later before Thursday. So let's say that I gave you a molecule like 2-butanol. So this is 2-butanol without any spatial information. It is C4 H3 4 6 9 10 O, right? Hopefully you guys can see that. And I'm going over this again to think about bond line drawings and make sure that we're all on the same page. And we're talking about stereoisomerism, right? And we're talking about carbons that can be chiral. There is a chiral carbon in 2-butanol, otherwise we wouldn't be talking about it, and it's here. And what makes it have chirality is that there are 4 unique groups on it. Okay? There are, if you draw this in a dash wedge type structure, you have that carbon, this one here. We'll draw the oxygen on top, the hydroxyl group. It also has a hydrogen, right? Because it's a bond line drawing. So we'll draw it, I don't know, we'll draw it here. And then it has 2 substituents. Look up here and tell me which substituents there are. There are 2. You can just think them, mutter them, yell them out loud. I don't care. All right, I'm hearing some things. It might be English. It might have said methyl and ethyl. Okay, there's a 1 methyl group, and there's 1 ethyl group coming off of that carbon. Hopefully you all see that. Do you see a methyl and ethyl? Because that's a chapter 4 thing, and we're using chapter 4 things in chapter 5, chapter 3 in chapter 5. We're using everything. So please make sure you're with me and stop me if you're not. So we have a methyl. We'll put it like this. Methyl. Because now we're going to start using some abbreviations. Just when it gets more fun, it couldn't get any more. It couldn't get funner. Yeah, I don't know, something that my dad used to say. Okay, so now you have the ethyl and the methyl. So my question to you is this R or is this S? And nobody's looked at the book, so you're all like, what? That's stupid. There are 3 steps you can follow. And if you follow those 3 steps, you will always get S and R correct. Always. I'm talking always. So, first step, assign priority. Figure out which ones are the highest priority and which ones are the lowest. It's pretty simple, actually. Highest atomic number means highest priority. Okay? Highest atomic number highest priority. And consequently, lowest number is what? Yeah, lowest priority. Great. We're all here. We're still alive. We're still awake. It's Tuesday. Lowest priority goes with the lowest atomic number. Who here knows the atomic number for hydrogen? Yeah? Number 1, right? Is it just one proton? Good. So that means it has the lowest atomic number and it has the lowest priority. So if you ever see a hydrogen, just go ahead and drop a 4 on it, because there's going to be 4 unique groups for a chiral center, chiral carbon, and the hydrogen always has lowest priority. So what has the highest priority? So tell me, somebody, what the highest priority substituent is. I don't know. Did I hear it? Does it have an oxygen? Yeah, you see it? Good. The alcohol group has the highest priority. So now, what about the methyl and the ethyl? That one's pretty easy, right? Except they're both carbons. When you have a tie, you have to go to a tiebreaker, just like you do in any other sport. And the second intermission. And to settle this tie, you have to do, I think the best way to do it is to draw the molecules again, or draw the molecule we're dealing with one more time, and this time to not use abbreviations and to use like a full second time. Now see, that's interesting. I wonder why it is doing it twice now, because it used to only do it once. I don't know, maybe this will be the thing that really pushes me over the edge. Okay, right, so I'm fine now. We're all fine. Everything's good. So you have one CH3 group, right? And then you have a CH2 group, and then we'll just call that CH3. Okay, so, okay, I'm on purpose using the type of drawing that gives the least amount of information. Are you all with me as to why? I just want the tiebreaker. I don't care about the rest of it. So if you look at, in fact, I'm just going to scribble these out because I don't care. So now, if you look at these carbons, each carbon is bound to the middle one. So these cancel out, right? But there are 3 other bonds, and that's what we use to figure out what has the highest priority. Because one carbon, this guy, has 3 H's that it's bound to. And the other one has 2 H's, but a carbon. So now that is a difference. And so just like before when we assigned highest priority, here in the tiebreaker, as soon as you find a place where there's a bond to something with a higher priority or a higher atomic number, then you assign that group highest priority. Maybe Siri will get the next time. Here we go. So because one carbon is bound to another carbon instead of just 3 hydrogens, this one has the highest priority, the ethyl group. So we're going to assign it number 2 and assign the methyl number 3. Is everybody with me on where that came from? I need you to look and make sure that you are right here at this point. Because if you don't see where these priorities come from, then the next step will be a lot trickier. Yeah, I'm seeing some nodding. Okay. Good. Step number 2. Again, this whole idea of like your mind's eye and trying to imagine holding one thing constant and rotating it, just like we did before, becomes very important. Because the second thing you do, I'm just going to use another sheet of paper because I have that luxury, is, I'll bring it over here. That way I remember where I'm at. All right, number 2. The hydrogen in the molecule, so let me redraw it so that we're all on the same page. So we were here. Right? Ethyl, methyl, and we had priorities assigned, and they were 1, 4, 2, and 3, just like that. The hydrogen must be on the dash. It has to be like away from you, if you can imagine it. So your job is to rotate until you have carbon hydrogen somehow. And you can do this a number of ways. As long as you hold one atom constant, you can rotate the molecule however else you want. Okay, whether that means holding the methyl constant and then rotating them all one way or the other, it doesn't really matter. But you need to develop in your mind this idea of turning these molecules. If there's nothing else that will help you more, there is nothing else that will help you more for chapter 5 in this class than this idea of being able to rotate a molecule in your head. There is also a resource available online. I meant to pull it up, but I didn't. So let me grab that real fast. It's from a professor from UCLA, and it is a fantastic way to get more problems of how to assign R and S, and it has a very nice user interface that you can use. Let me pull it up real fast and show you. There we go. Okay, RS chemistry. There we go. All right. Great. So there's this great website called rschemistry.com. This is an aside, a free plug, free advertisement for them. It's from this professor, Neil Garg. You can learn how to do this. Ooh, there's sound. I did this before. It was muted. This is great. All right. So if we just say we want to do easy, they'll teach us what a stereo center is. They'll tell us how to assign it. And they'll give us very nice introductions, much better than I'm doing today. And I don't have music, so this will be a lot more engaging, right? And so you go through this whole thing, and then you'll be able to play. You know, they've really gamified this idea of finding stereo centers. So here's Adderall. That's fun. Let's find priorities. That looks like number 1. That looks like number 2, 3, 4. Seems like I got it right. Okay, good. Complete the new rejection. So they do it this way where the hydrogen is pointed away from you. So it's behind this carbon. And now you put, let's see, you drag and drop 1, 2, and 3, assuming 4 is in the back. Okay, 1, 2, all right. Assume 4 is in the back, so 2 is on the left, right? So if 4 is in the back, 2 has to be on the left, and 3 has to be on the right. Do you all see that? Again, idea is mind's eye. If you play this game, maybe you'll develop it faster than just looking at your textbook, because that's boring. There you go. 3 go counterclockwise, which is left. Yes. Look at that. I got it right. So please, if you find the textbook boring in this section, go to LEcture14 and just play the game. For this part, this is really nice. You know, I did this before and I was like, where was this when I was doing this? All right. Right. So, just like they did in that fun game that I now feel very insecure about, we have to put the hydrogen in the back. Okay? So, let's rotate something to put the hydrogen on the dash. Hold up a finger and tell me which one you want to hold still. 1, 2, or 3. I don't care. It doesn't matter. I'm seeing some 1s. I'm seeing some 2s. It looks like the 1s have it. So we're going to go with 1. We're going to hold 1 steady, like on top, and we're just going to rotate it like a top. Okay? So bear with me here. Holding 1 steady, so let's redraw that first. And I'm going to do it in blue. There we go. Now we have moved this. Let's say we moved it to the left because that's less movement and I'm lazy. So this is now the H. Since we moved it left 1 position, everything shifts 1 position. So now the ethyl is in the dash and the methyl is in this position, right? All right, so then the H is in the dash like we wanted. Let's reassign priority. 1, the ethyl was number 2, methyl is number 3, and hydrogen is number 4. So, I have never thought to teach it like a Newman projection, but seeing as the game was so helpful, why don't we just do that? So now what I suggest, this is not in your book, but it is in the game. I suggest to make a small Newman projection where you are looking, let's do it in red. You are looking down the molecule between the CH bond. Does everybody get that? Down the molecule, down the CH bond. Okay, so then redrawing that, let's draw the molecule. So now this is the bond we're looking down. Again, it's the CH bond. And the OH group is pointed up, right? So now, if we are looking down the molecule and the OH group is pointed up, to me it looks like there are 2 here, and the ethyl group is here on one side, right? On the left, and the methyl group is on the right. Everybody see that? I'm trying to get your spatial muscles working here. All right, so the ethyl is over here, and the methyl is here. That's what I did before, right, with this? I get confused because this feels like different than when we're up here. Anyway. So now we have these guys. We reassign the priority, 1, 2, and 3. And now we come to the 3rd step. And this is why being sure you can visualize in your head how to rotate things is very important. Because the 3rd step is to assign clockwise rotation or counterclockwise rotation. If they go clockwise, that's to the right, clockwise, sorry, to the right for you guys, clockwise, that means R. If they go to the left or counterclockwise, that means S. So in this case, I shouldn't have drawn that because that's confusing. In this case, the rotation is from 1 to 2, as it always is. You go from 1 to 2 to 3. And because it's to the left and counterclockwise, it is S. So if you follow these steps, you will always get R and S right. And then you will be really great organic chemists, because I think probably this is one of the things that trip people up the most, and then they get anxious and upset. But you guys are going to play that game, rschemistry.com. you're going to practice a lot in your textbook of chapter 4 and 5, and you're going to have a really good Tuesday and Wednesday because we're out of time.